After you have decided the amount of reinforcement bar to be provided in the slab, and after you have checked the shear resistance to be adequate, that means you have completed the design for the ultimate limit state, particularly for the moment and shear resistance. Our next step will go for serviceability requirements. In this question, you are asked to determine the maximum spacing of the reinforcement and check if the maximum spacing is exceeded. First, you will need to know what is the purpose of having this maximum spacing of reinforcement. It is a way used to control the cracking due to loading. The cracking can be due to the loading as well as the shrinkage or thermal movement. You would like to ensure that the cracking are properly controlled. For a typical reinforced concrete member, the maximum crack width is set to be less than 0.3 mm. This is to ensure sufficient durability of that particular structural element. In fact, there are two ways to control the cracking. First is by determining the minimum area of reinforcement. This can be done by using the equation here. Now, as far as the revisions question is concerned, we have deal with the maximum and minimum bar areas in the design of the beam B1 to 4. A typical final exam normally will not assess the same thing twice. But if you wish to know the process to determine the minimum bar areas, you can simply adopt these equations and also the ratio given here. Based on the compressions of the concrete given, you find the FCTM. You can get the FCTM from table 3.1 in Eurocode 2, or you may adopt the equation here if the concrete grade is less than 50. And then the FYK, it will be the specified yield strength for the reinforcement used in the slab, which is 500 Newton per mm square. The B here, it will be 1000 mm, which we are calculating on the basis of the 1 meter unit width. And then the depth, it will be the one that we have calculated previously, equals to 115 mm. Substitute the equations, you will get the AS minimum. You will need to check your AS minimum against your AS provided. See if the AS provided is sufficient. The AS provided should theoretically be greater than the AS minimum. And if you are using the ratio here, the ratio varies on the basis of the concrete grade. Let's say this question, the FCK is equals to 30. That means the ratio now it would be 0.0015. That means 0.15% of the effective areas of the slab shall be the AS min. Again, the B is equals to 1000 and the depth it will be equals to 115 as calculated earlier on. You may compare the AS min found from the equations against found based on the ratios. They vary slightly. To be safe, you use the bigger value of the AS min to be checked against your AS provided. Now you might want to ask, where do you get this ratio? In fact, you don't find this from Eurocode, but you see this in some references for reinforced concrete design. I believe this is inherited from the previous standard, probably British Standard at 110. This I'm not quite sure. probably you can check and let me know where do you get these ratios. And the minimum bar area for the slab, which we are referring to the secondary reinforcement, it should be at least greater than 20% of the main bar. By right, you will have to design the slab in both the longer span and the shorter span. When the ratio varies, the provided amount of reinforcement bar may vary. At the end of the day, you will have the design reinforcement in the shorter span and also the longer span, both at the support and also at the mid-span. You know that the shorter span, it will be the main reinforcement, and then the secondary reinforcement, it will be at the longer span. Whatever reinforcement that you found in the longer span, you will need to make sure the provided amount of reinforcement bar needs to be greater than 20% of your main bars. This is not only applicable for two-way slabs, where you will have bending moment diagram both at the shorter span and also the longer span. This requirement of 20% of the main bar as the secondary rebar is also applicable to one-way slab. One-way slab happens when the Ly is more than 2 times greater than the Lx. When the slab is considered one-way, that means you're going to expect bending moment diagram only at the shorter span. The slab is only subjected to the bending to the shorter span, whereas in the longer span, the bending moment, it will be negligible. In this case, most probably you do not need to design for the resistance of the moment in the longer span, as you cannot find any bending moment when the slab is in the longer span when it comes to one-way slab. With that, you can simply adopt that 20% of the main bar as the secondary rebar for the slab. This settles the cracking control due to the minimum bar areas. The calculation step is not demonstrated here, as this example is meant for revisions for final exam. When we have deal with the minimum bar area for the beam, normally you will not expect it to appear again for the slab design. Of course, it is possible to have the checking for the minimum bar area appear in the slab but not in the beam. One way or another, you need to get yourself prepared. Coming back to the maximum spacing, which is the second method to control the cracking. Both methods apply to the slab. For a typical design, you need to make sure both are fulfilled. Now, when you need to determine the maximum spacing of the reinforcement, there are two methods. First is by referring to table 7.3n, where you need to estimate the stress in the steel reinforcement. These equations shall be used to determine the stress in the steel, which is on the basis of quasi-permanent load against the ultimate limit load. Based on the steel stress calculated, refers to the table with the crack width of 0.3 mm, determine the maximum spacing for the reinforcement. This is the first method, and this method does not apply to the slab less than 200 mm thickness, which in this question, the slab that you need to design, the thickness is 150 mm. It is thinner than 200 mm. With that, you're going to apply the second method specifically for the slab less than 200 mm thickness. The requirements are stated here. You have the main reinforcement and secondary reinforcement. The main reinforcement applies to the shorter span, which is a more critical directions, whereas the secondary reinforcement shall apply to the longer span, the directions which is not as critical. Since that the example here we are designing for the main reinforcement, that means the requirement for the maximum spacing shall refers to the conditions of the longitudinal reinforcement. The maximum spacing shall not exceed 3 times the slab depth or 400 mm. In other words, we are looking at 3 times of the H or 400 mm. Use the smaller value to define the maximum spacing. The H, it will be the thickness of the slab, which is 150. That gives you 450 and 400. The smaller value, it will be 400 mm. The AS provided with the spacing of 350, which we have decided in our previous question. Now you will check this 350 against the maximum spacing of 400. The provided spacing is less than the maximum spacing of 400. Therefore, the maximum spacing check pass. By right, you will have to also check for the maximum spacing in the secondary reinforcement. The maximum spacing is slightly larger, which is 3.5 times the slab depth or 450. Since the questions does not ask for that, we do not demonstrate the solutions for the secondary reinforcement. But this is for your knowledge. In fact, there are other serviceability requirements for the slab. Among those relevant, it will be the concrete cover. In these questions, the concrete cover has already been given. Therefore, you do not need to calculate the concrete cover. In the case it is being asked in the question, you may refer to the Eurocode, clause 4.4.1.1, equations 4.1 to determine the concrete cover. The concrete cover is determined by C-mean and the deviations. The deviations is typically taken as 10 mm as recommended by Eurocode 2. As for the minimum concrete cover, you may refer to equations 4.2, which is governed by 3 main aspects. The minimum cover due to the bond requirement, the minimum cover due to environmental conditions, and also at least 10 mm minimum cover. For more details, you may refer to the Eurocode and also our previous videos. How do you determine the C-mean B, C-mean durability, and so on so forth. Other than that, there are minimum spacing for the reinforcement. This is not critical for the slab, as you know that the slab element have relatively large section as compared to the reinforcement provided. The reinforcement provided in the slab is not likely to be congested. Therefore, most likely you will not be asked to determine the minimum spacing for the slab design. Minimum bar area probably, as you're going to expect that sometimes the reinforcement provided may be less than the minimum bar areas required. In order to prevent providing the reinforcement less than the minimum bar area, normally you should check for the minimum bar area. As for the maximum bar area, although the requirement for the maximum bar areas for the slab, it would be same as the beam, which we are talking about not exceeding 4% of the cross-sectional areas of the member. Most likely the maximum bar areas will not be exceeded. The chances of having this come out for the slab design, it will be quite slim as far as final exam is concerned. How about the maximum bar size? The maximum bar size is meant for crack control. You will need to estimate the stress in the steel bars and then determine the maximum bar size. This may not be an issue because normally when we provide the reinforcement for the slab, we tend to use smaller bar size. For a typical high-yield steel bar, we will provide 10 mm bar diameter. This will be the smallest bar size used for the slab in general practice. Most likely this will not be assessed when come to this slab design. Even if it is assessed, there is very high chance that the maximum bar size will not be exceeded. The side face reinforcement is not applicable for the slab design. The surface reinforcement is also not applicable for the slab design, and the deflection check is very important to the slab. The deflections we are referring to the L per D ratio. Compared to the beam, normally the effective depth of the slab is smaller. For the beam and slab of the same span, the slab is likely to be more critical. You might need to check for the deflections. Bear in mind that when you are checking the deflections, you are checking it in the shorter span. As the deflections is more likely and more critical in the shorter span than the longer span. Why is it so? Or if you have difficulty determining which directions you need to check for the deflection, you can take one-way slab as the extreme case. Try to imagine a one-way slab where the shorter span is limited and the longer span is unlimited. Imagine how the slab shall deflect. A typical slab will undergo deflections in the weaker directions. You need to know that the slab is monolithically cast together with the beam. This is to ensure that the stress can effectively distribute from the slab to the beam. If you observe the reinforcement in the beam and the slab, taking this end as an example, this is the beam and this is the slab. You will have your shear link here and your compression steel bars here. You will see the reinforcement is a part of the slab here. They are monolithically cast. That means they stay intact under normal circumstances. Now when the slab and the beam is well intact, that means the beam can be used to restrain the deflections of the slab. The longer span will have a stronger resistance or restraint to the slab, preventing it from undergoing excessive deflection. Whereas the shorter span, the restraint is not as significant as compared to the longer span. Now imagine you have limited span at the shorter directions and unlimited span in the longer directions. For example, you consider this as one piece of slab without any beam here. You're going to imagine how the slab should deform. Draw a straight line at 40 degrees from the corners. This will represent the directions of the bending. The bending, it will be on this side instead of on this side. With that, you know that the deflections, it will be more critical towards the shorter span. Therefore, when you are checking the deflections in terms of the L per D ratio, you only need to check for the shorter span. For more details regarding this, you may refer to our previous examples discussed in Chapter 8 regarding the slab design, which will provide a table for the checking under different circumstances for two-way slab in the LX and LY. Checking for the deflections, we are looking at the shorter span. This table also summarizes what we have discussed just now regarding the checking for the AS minimum, AS maximum, maximum spacing, and the minimum spacing. If you know the concept, you will know which one it will be more critical to which directions.